Hello, my name is Vittorio Basso, and these are lectures that I record for the project TRaMM, project of metrology for the dissemination of the methods of the measurement of the magnetic field. These lectures are organized in, say, 4 different recordings, subdivided by different topics. The topic is very vast, so the name is Principle of Magnetic Field Measurement. In the first part, we will try to describe the generation, what are the standards, and how the metrology of the magnetic field is performed. In the second part, which is more practical, we dedicate to measurement methods and different kind of instrumentation which is used. Let's start with part 1, that also is divided in 2 blocks. In the first part, essentially, we will deal with metrology of the magnetic field. So when we talk about metrology, we have essentially a certain issues that we have to remember. First, we have to define the quantity that we have to measure. So that's the definition, which is found in GUM. The measurand for us is the magnetic field. The measurement is a process of obtaining this value that are attributed to the quantity. The traceability is an important issue for metrology. So how do we establish the chain of calibration that link the measurement quantity to the set of constant that we have? And also another important issue is the uncertainty, the parameter that characterizes the dispersion of the measurand. So first, we will dedicate some time to the quantity, the magnetic field, and especially to the theories, to the equation where this magnetic field appears. We have essentially 2 that we will use. The Maxwell equation, so the equation for the electromagnetic field, and the phenomenon of magnetic resonance. We will see that most of the effects of the methods that are used to characterize and also to address the metrology of the magnetic field are based on these 2 physical effects. We start from the Maxwell equation. So we have the Maxwell equation written here. These are the equation in vacuum. So these are essentially the equation for two quantities, 2 fields, the electric field and the magnetic induction field. These fields are vectors. They are defined in space, in the free space. With these 4 equations, essentially, we have the connection between the fields and the sources. Hence, being these field vectors, the equation does also define some geometrical properties of the fields in space. So the first equation is the Gauss law that essentially says that the sources of the electric fields are the electric charge density, but it's the divergence of the field, of the electric field, which is equal to the charges. The second takes also the divergence of the magnetic induction field, but this divergence is equal to 0. So we have no charges. We have no source charges for the magnetic field, for the magnetic induction field. Then we have the Faraday law and, let's say, the Ampere law plus the Maxwell terms that relates the vectors to the time derivatives. But also, with the Ampere law, we have a connection of the curl of the magnetic induction field with the electric current density. In these equations, we have not only fields, sources, but we have also constants. So what do we have? We have essentially the permittivity and permeability of vacuum that are constants, essentially fixed. The speed of light is 1 over the square root of the product of the 2, and the magnetic constant used to be a numerical constant, 4 pi 10 to the minus 7 in the international system. we may wonder if these Maxwell equations are a fundamental theory. So if we can say that electromagnetism is one of the fundamental theory of physics or not. Well, it used to be something like that, but now we cannot say this anymore, because with the revision of the international system, with the fixing of the constant, the fixing of the elementary charge has made a change in the Maxwell equation, so that this is no more a true fundamental theory. Why is like that? Because essentially in the international system, we had before a complete correspondence with the GGS system, that in a certain sense was most liked by physicists, because it only included the speed of light as a constant inside. Now the point is that we cannot fix at the same time mu0 and the elementary charge. And so in the new international system, mu0 is no more a numerical constant, but is still a constant, but something that has to be measured. This is the value which is reported as the most accurate one, so we can still use the 4 pi, but in a sense we have to introduce an uncertainty for this value, which is indeed very small. Why do we have this? Essentially because we have a relation involving the permittivity of vacuum, Planck constant, speed of light, elementary charge, and the fine structure constant. So the two, the mu0 and alpha, they are related to each other. Fine structure constant is very well known, is a constant that has to do with quantum electrodynamics. It enters in many physical phenomena, high energy physics, atomic physics, cosmology. So as the two have to be related, then the uncertainty of the two is related. That's the reason why mu0 is related to alpha and cannot be fixed anymore. Well, this is something which is important from the basic point of view, but not really relevant what concerns to metrology, as the uncertainty introduced by having this measurable value of mu0 is 10 to the minus 10, so something very small. So what we had still to add regarding the Maxwell equation? Well, essentially that we have seen the equation in vacuum, but it's also very important to write the equation in matter, where we have not only, let's say, empty space with some point charges with their speed, but also we have the matter. And the matter can magnetize and polarize, so it can develop spontaneous or induced or polarization and a magnetization. If we have these two, then we have to rewrite the equation, and the result of this rewriting is that we cannot anymore use just the electric field and the magnetic induction field as we have done before. But it's better if we introduce this polarization field describing the matter, this magnetization field describing the magnetized matter, but also introduce other fields that are called the magnetic field and the H and the electric displacement D, that are auxiliary field, but very helpful, because then we can write the equations of Maxwell in terms of true electric charge density and true electric currents. And then we put all the effects of the matter inside the vector D and inside the vector, let's say, M or H. We have still to remember that this Maxwell equation, we don't see the atomic level. So in any case, the vectors and the quantities that we have introduced are the results of some moving averages. So we don't see atoms, we don't see, we describe the matter as a continuous medium. And this is very important to remember. Well, this is important to say because then the relation between the magnetization of something and the magnetic field will always be given by susceptibility. When we work in air, the susceptibility is not zero. air a very small positive susceptibility. For example, water has a negative susceptibility, it's a diamagnet. So this is something, even if very small, that should always kept in mind. Why these Maxwell equations are useful for measuring the magnetic field or the magnetic induction field? Because we can exploit the integrated form of the Faraday law and the Ampere law. So take the Faraday law, make the circuitation of the electric field on a circuit, on a closed circuit, and you will discover that this is related to time change, time derivative of an integral of a surface of the magnetic induction field. This is the magnetic flux. As the circuitation of electric field is something related to some electromagnetic force, then we can measure the variation in time of the magnetic flux by electrical means. Similarly, with the Ampere's law, we can make the circuitation of the magnetic field this time, and this circuitation will be related to the integral of the electric current density over the surface that is defined by the circuits. This is nothing else than the Ampere law in the usual form, and so we have that field is related to the current, electric current in the conductor. In practice, what do we have? We have that the method of pickup coil, as said before, we can, if we are able to measure the electromagnetic force, for example by a voltmeter, on a pickup coil, if we know this, we are able to measure the flux, and if we know the surface, to measure the magnetic induction field, which is concatenated with the pickup coil. At the same time, as we have a relation between current and the magnetic field H, we can use coils, solenoids, or more complicated things in order to relate the current and the magnetic field. So we not only generate in this way a magnetic field, but also we know the value, because there is a relation between them which is completely geometrical. The point now is with the solenoid, with the coils, we can generate this magnetic field, but the question is how uniform this magnetic field is if we want to have standard. So a standard relation between the current and the magnetic field in a certain region of space. So to make an example, if we take a current loop, the field is very non-uniform in space. So it goes down very quickly if we displace from the center of the current loop. So we could say that the individual current loop is not good source of magnetic field and not good object for making a metrology for the magnetic field. Little bit more complicated is to use a couple of current loops. This is called the Helmholtz coil. So instead of a single loop, we can make let's say a small winding with a certain number of turns. What occurs that is the uniformity of the magnetic field in the center can be very much improved with certain conditions, and this condition is the so-called Helmholtz condition, where the distance between the two pair of coils is exactly equal to the radius. You see in the plots the distribution of the field as a function of the distance of the center. If the coils are too far from each other, the field goes down. If they are too close, it will increase too much, but then it becomes uniform. So with this optimal condition, we get a very large uniformity. So this can be an apparatus able to generate magnetic field, not too large magnetic field, say typically below 10 millitesla, that can be uniform enough to provide the traceability of, for example, a magnetic field sensor. In practice, these are the typical coils that can be manufactured. So in the left, there is one set of Helmholtz coil with some probe measuring the magnetic field that can be traced to the current. So in the middle, on the right-hand side, there is a setup made of 3 Helmholtz coils, one inside the other, for let's say that can be useful for many things, as we will see later. Regarding metrology, what is commonly done is to realize Helmholtz coils of the kind just described, to know very well the calibration constant, and then to use this as a reference. And this is the case what we have in INRIM in Italy as the standard coils. We have a couple of them, one for very low fields, one for larger fields. Uniformity is clearly different, and so this uniformity provides, let's say, one of the main sources of the uncertainty of the magnetic field that is, let's say, measured in this way. Clearly depends on the size of the probe that is put inside. There are other opportunities, for example, for improving the uniformity, and this is the uses of solenoids. So if instead of having just a couple of turns, we use a continuous set of turns and we build a solenoid, then uniformity can be improved very much. At the practical cost of having no possible accessible area apart, access to the center of the solenoid apart from the axis. And this is one of the limitations and one of the advantages of using Helmholtz coil. The uniformity depends on the ratio between the length and the radius of the solenoid, and it can be improved very, very, very much. And the coil constant essentially is given by the formula written there. Well, solenoids are very important because highly uniform solenoids are those that were used very much in metrology for having very large field uniformity. The coil constant can be determined with very, let's say, high accuracy. There are methods, for example, methods divided by carat in this paper written there, where let's say, the uniformity of solenoids can be improved also by changing the density of the turns along the length. In the pictures you see in the left, very precise solenoid that is being used to determine the precession frequency of the proton in the 70s and the 80s, essentially done at NIST in the USA. At the right-hand side you have an example where, for example, these methods can be used for generate fixed gradients that could be also important. What we can add? Well, for example, one of the issues of metrology could be to use a measuring instrument, for example, what is commonly called the Gauss meter, so still using the name of the units Gauss that is in the GGS, but this is a common name that you will see in measuring instruments. And you want, for example, to calibrate this Gauss meter against some standard. Standard, for example, made by a solenoid or by a Helmholtz coil, as we have seen before. So, can we just take this Gauss meter and put it into the standard and that's it? Well, it's not exactly like that. And there is one very important issue that we have to discuss before just making this calibration. And the issue is that the source of the magnetic field is not only our solenoid, but we have a lot of other sources around. And one of the most important sources around is the Earth magnetic field that we cannot avoid to have. So here is a map of the magnetic field on the planet Earth at the surface. Typical values are around, let's say, the modulus, a little bit less than 50 microtesla, is a not so small value. So when we want to calibrate a probe, we have also always to take into account that we are immersed in this magnetic field. So the point is that if we want to calibrate a probe, we have to take care of this, for example, by eliminating these hurt magnetic fields. Good point is that there are measuring instruments, is called the flux gate. We will see them in one of the next parts, that are very sensitive to very low field, and their built-in principle is such that they are very good in measuring zero fields. Let's say that even if they need calibration, they are precise for zero. So they can be used as sort of a null indicator. So if we have an instrument like this, then we can possibly measure the magnetic field generated by the environment, by the planet Earth itself, or by other sources, and to compensate. Compensation system is crucial because the quality of the compensation is also the quality of the measurements then. If we don't compensate well, it means that the value of the field that is not compensated goes as uncertainty in our measurement system. In the example that we see here is the method which is developed in the UK, the Bushy houses, where this is a beautiful villa in the park, where far from any sources, electrical sources, there is this quite large compensation system which is driven actively. So there is a measurement instrument measuring the magnetic field of Earth and also its small fluctuations in time, and able to correct it. So these fluctuations are not that small, so we have seen that the big part is around 50 microtesla. So if we compensate this big part, something remains, and this remaining is around 15, 30, up to 50 nanotesla now. If we still compensate actively, we can go down by, again, factor 10. So having a fluctuation of this compensation of this environmental field, which is very, very small. So increasing and decreasing a lot the uncertainty of the magnetic field. These compensation systems are quite widespread. This is the system that we have in EMPIR in Italy. So a standard coil should be inside a compensation system in order to, let's say, eliminate actively the effect of the environment. So we are going to conclude this first part, and let's say we touch a little bit an issue related to uncertainty. So this is a typical exercise that we can do. For example, when we want to use a standard coil to calibrate an instrument, and what is the typical uncertainty budget that we have. So suppose that we receive a coil with a calibration certificate. This coil is made to provide a magnetic field of 1 millitesla. We measure the current by using a standard resistor of 1 ohm. And so we can have a look to the uncertainty budget and just to have an idea where the main contribution to the uncertainty they come from. And we see that, let's say, the main 2 points is essentially the ambient field. So if we are very good to compensate the ambient field, we can decrease very much the uncertainty that we get. The same thing, it occurs is, for example, we want to calibrate another coil by using the instruments that we have just calibrated with our standard. So suppose we have our calibrated instrument, we have built another coil, and we want to calibrate the coil, for example, to use as a for a customer or for another institute needing standard and so on. Again, we have the same problem. if we have a look at the uncertainty budget, we see that the main contribution to the uncertainty is again the ambient field, because this is another measurement that we have to do, again, that we have to do in the compensation, inside the compensation call, and that's it. So the point here is that this essentially the ambient field and the uniformity of the fields are the two main issues. To conclude this part, let's say that this is what is typically done in a metrology institute. For example, the system used here in TRaMM, we have coils, our standard coils that have been calibrated against the standard coil, which was a traveling standard, in that case a few years ago, came in from PTB. And so you can see the typical values that of the uncertainty that, let's say, come from the standard coil, goes to the measuring instrument, and then they go to the coil to be calibrated in TRaMM. So this is a typical uncertainty budget that's and uncertainty and issues that we have when we have to calibrate coils with instruments. Okay, and for the first part, we stop here.